squishy things. All right, live videos rolling. Cool. Thanks everybody for coming. I'm so excited. What? I'm so excited that you all could be here. This is the first time I've ever done something like this, where it's like a public workshop and I had to advertise it and everything myself, and I didn't know how it was going to go. But I'm glad that you all are here. For the physics of relationship, we're going to do this in 2 parts and have a break so people can like stretch their legs and go to the bathroom, get more food and whatnot after about an hour. But before we started, I was hoping we could all just go around and introduce ourselves a little bit, say who you are, whatever that means, and like what brought you to this particular subject matter. Or you can just say that I brought you here, I guess. So I'll start. My name is Elliot, as you all know, and probably what brought me to this subject matter is like a confluence of my entire life. But I would say learning about fungal networks in college in the biomimicry club, while simultaneously getting a physics degree, is what led me to this workshop. And that's like the nutshell version. Yeah.
My name is Summer. Hello, everyone. I'm Elliot's partner, and he's been doing these workshops for a few years, pretty much since I got to know him, and I haven't had the opportunity to attend one, so I am here. And I also just kind of go where he goes a lot of times. So I'm here.
Hello, I'm Tyler, and I've known Elliot through Rise and Sonic Bloom. And I wanted to take this workshop at Sonic Bloom this year, but I was just so burned out from the Permaculture Academy that I'm glad he's offering it now, and I can see it now. Nice.
Welcome. We're just going around saying your name and what brought you to this subject matter of this workshop today. And also, Eugene, if you want any food, we got plenty of food back there, so you can go for it. Sure. And you're up in the rotation.
Oh, damn. Yeah. I'm Eugene. I'm just intrigued. I like one of those NF types in the Myers-Briggs, the idealist thing. And so combining things like this is awesome to me. So, and I still live in my car.
Yeah, it's running great. You may have seen it parked right on the street.
I actually didn't. I'm glad to hear that.
Well, my name's Mike. My friend Braden brought me to the presentation, but quite a few D&D brought me to Braden, so I'd say D&D brought me to the presentation.
Awesome.
I think it's actually pretty accurate, accurate in terms of D&D relationships. So it works out. So
Great.
Yep. I'm Scott, and when Elliot invites me to something, I try to go.
Fair enough. I'm Lois, and I'm curious as to what Elliot has to say in the physics of relationship.
I'm a previous roommate of Elliot, and I just wanted to see them again. And I actually specifically wanted to see this workshop because I read it and it sounded really interesting.
Thank you.
My name is Braden. I am a photographer by day, activist by night, and sometimes it swaps. I guess talked to Elliot a little bit about this workshop when he was gonna go do it at, was it Sonic Boom?
Sonic Boom.
And was interested then, and so decided to come and hear the whole thing.
Awesome. Well, thanks everyone. Let's jump right in. So we have these 2 primary words here, physics and relationship, which are like the anchor of what we're doing. So I want to start just by seeing if we can get on the same page for what these things actually are. So does anyone want to venture their definition of physics?
How physical things interact.
How physical things interact. Okay. Anything else? Anyone want to add to that? Refute it? What about metaphysics? Would you consider that outside of physics? Because about like mental things?
Are you asking me?
I'm asking you.
I am not enough of a physics student to answer that question with any degree of insight.
Well, it would depend a lot on like who you asked, and some people would say one thing and some people would say another, and that's going to be kind of consistent throughout this workshop and presentation, is that I might say something that doesn't seem right to you, and you're entitled to that. And the part of what inspires me to do this workshop is that I feel like it's kind of like at the cutting edge or like the bleeding edge of our knowledge and understanding. So naturally, whenever you do anything in that space, there's going to be a lot of disagreement because a lot of things aren't figured out already. But how I'll define physics is just like the rules that govern things. That govern things. So that could be physical things, like Scott was saying, or it could be like invisible structures, like could be laws, would be like a type of social physics in this like definition. But it's just the rules that govern like how things behave over time. How about relationship? What does it mean to be in relationship? Anyone can just shout it out.
Connections between people.
Connections between people.
Definitely. Or places or things.
Connections between places and things. Okay. Anyone want to like extend that? Have any other notions of what a relationship is?
Connections between any two.
Okay.
Of entities.
So you've all said connection, so let's dive into that. What does it mean to be connected?
Well, there's many different types of connections. There's emotional, spiritual, physical connections, birth connections, friend. There's just so many different types.
Different types. What holds them together? Why do we call them all connections?
Two aspects. There's at least two aspects.
Like two different things participating?
Yeah, they have to interact, and there has to be at least more than one.
Right.
I mean, the moon and the earth are in relationship, in connection or connectivity, but they don't touch.
Right.
They don't even come close.
Yeah, definitely. So this element of two things, at least two things, so I'll just say 2 plus things that are connected. And like Mike was saying, there's lots of different ways that things can be connected to each other. So they can be exchanging things. So like by exchange, so for example, I can be in relationship with the store when I give them money in exchange for goods, or I could be in relationship with, or like, let's say fire could be in relationship with food that you're cooking because giving it like that thermal energy that allows it to cook. So you can exchange energy or materials basically by exchanging energy or materials. And you can also be in relationship just by exerting what I'll just call a field on each other. So you can affect something without actually giving it anything per se. So exerting a field would be like the Earth and the Moon example. The Moon is in the Earth's gravitational field and orbiting around the Earth. And in that relationship, they are exchanging to a certain degree because there's friction involved, so they're like exchanging heat a little bit. But more so, they're just affecting one another's like states and energy levels. Okay, so we're gonna dive a lot deeper, particularly into like what different types of things can be exchanged and what it means for things to be in relationship. But I just wanted to lay down those fundamentals. Where did my thing go?
Your wife is
I'm
sorry
sorry
to
to interrupt, guys.
Oh,
Is there
yeah.
anyone with the green Honda in the driveway?
Oh yeah. No.
Maybe it's somebody upstairs.
Yeah.
Okay, sorry to interrupt, guys.
Oh, you're all good. Yeah, I forgot to announce no parking in like the circle thing at the end of the road. Is anyone parked in there either? Cool. Y'all are great at following directions. Okay. So there's just like there's lots of types of relationships, there's also lots of types of physics, and there's lots of things that are considered physics that kind of address different types of rules between different types of objects. So I give the example that maybe laws could be considered a type of physics, but typically we're going to think of like classical mechanics, quantum mechanics, things like that. So I'm going to call these lenses. There's lots of different lenses that we can look through when we talk about physics. So I just named a couple. Does anyone have any other like lenses of physics that you might be familiar with? So any like, what I'm asking is a school of thought. A lens is kind of how you're looking at, it defines how you look at a certain problem. So it would be different types of physics that define how you're looking at any kind of problem.
String theory?
mathematical string theory. Yeah. Quantum mechanics would be another lens. Classical mechanics would be another one. There's a big one that's going to be the focus of this entire workshop that no one has said.
What about magic?
Who's going to make it? Magic is definitely one, or like metaphysics, which basically just means outside physics. It's things that people accept happen, but they have no way of like explaining them. Social elements, definitely. So like sociology or even ecology could be a lens. There's a big one that's under just regular old physics that we're missing. And that's why I'm talking about it, is because people don't talk about it, even though it's pretty much the most fundamental of all of them. Okay, it's thermodynamics. Thermodynamics, which basically means energy motion. Thermodynamics, energy exchanges and energy moving around. So thermodynamics is going to be the main lens that we look through in this workshop. But as I already stated, it's important to understand that each of these lenses kind of offers a different way of looking at a problem. It's not that one's right or one's wrong per se, but they just give different types of explanations. And you might use one in one circumstance and not use it in a different circumstance. So for example, classical mechanics is pretty useful for like everyday physical interactions. If I throw a ball or drop something, it's useful in describing those and can describe them super accurately. Quantum mechanics would be one where you're describing things that act as waves or describing very tiny things. And quantum mechanics can describe a lot of other things as well. And then one other one I was going to mention, like metaphysics would be one when we're trying to describe or explain things that are basically outside of all of our other lenses. Metaphysics is this big bucket category for things that we don't understand. That's why it's called metaphysics, the outside of physics. And of course, any physics that is like accurate is going to have to include things that are currently outside of physics in order to have full explanatory power. And I think that, in my view, thermodynamics is probably the one that has the greatest promise for explaining those, and the reason is because it's the most fundamental. So, in fact, all of pretty much modern physics can be derived from a single equation, which is from thermodynamics, that we're going to get to in a second, or more than a second, obviously. But okay, let's see. Okay, we already kind of talked about these. Okay. In the second part, after we do our break, we're going to be talking about like system dynamics and fractal patterns. So we're going to be, in the first section, we're going to be talking about like the very basic fundamentals, pretty much all about that one equation from thermodynamics and how it causes all sorts of different activity and behaviors in the world. And in the next one, we're going to analyze entire systems from that perspective. But before we get there, I just wanted to define and give a little bit of insight into systems and systems thinking. So what is a system? Anyone?
A process or method that accurately and predictably gets you to a set goal.
Okay, so it's like a set of things that create a certain outcome?
Yes.
Okay, Ryan?
A set of things that are all internally coherent.
What do you mean by coherent?
Like they all like cohere with one, like they don't contradict one another or like work with one another.
They work
Okay.
in conjunction or harmony.
Mm-hmm.
Okay.
We're talking about functional systems here. There's a lot of dysfunctional systems.
Okay, so how would you modify that definition to include dysfunctional ones?
Organization of working parts.
An organization of working parts? Okay, yeah. So things that are like interacting with each other. I was looking for something very basic, which is just like a set of relationships. It's at its basic level, it's like one relationship is two things interacting with each other. That could be a system unto itself, or a system could include a lot of other things that are also interacting with each other. And hopefully they're interacting like in coherence with each other and maybe producing some desired outcome for us. But sometimes they're like kind of chaotic, and a lot of what the system does depends on the boundary that you have. So a system is just a collection of relationships that we define together for some reason. And it's probably just because we're interested in them. But the boundary point of a system, so that's like what is included in the relationships and what is excluded from those relationships, is ultimately arbitrary. And you define that boundary just based on what kind of questions you want to ask about the things that you're looking at. So you can always expand or shrink your system boundary, and what will happen is it will reveal different things to you based on what scale you look at it at. So if we view like a city as one system, and we define like the boundaries of the system as the outside of the city, and we try to study like how the city behaves, we'll get very different insights than if we look at a system as an individual, which is within that city and has a collection of relationships unto themselves. And so how we define that boundary is going to impact a lot kind of what we learn from the system. And systems, in systems thinking, generally we think of a system as having like a goal or having rules or having some kind of outcome. So it's producing some kind of net behavior. So we could draw like a box and say, this is our system. You know, it's got something here, maybe stuff is flowing this way and this way. Maybe we've got another one that's floating over here or something. And then in general, we're gonna have like one set of things coming in, inputs, and one set of things coming out. And our boundary is going to determine what's considered like an input and output of the system. So if something is outside of the system, that basically means we don't care about how it impacts what's inside, or we're considering that it impacts everything the same. So if, for example, if we look at the Earth and the sun, and we consider the Earth one system, and the sun then would be outside of our system, we're assuming that the sun is impacting the Earth like in the same way across the entire Earth. You know, we could estimate however many watts of power the sun gives the Earth. That's just how we consider like the Earth is operating as a system. And of course, you can have systems within systems. So you could define like a subsystem that is these four, and then ask how it relates to the system outside of it. So the main point I want to get across here is like what the dynamics of the system are depends on the boundaries that you define and consider like inside and outside of the system. And it's going to reveal much different things depending on what those boundaries are. And the rules of the system might even be different depending on what the boundaries are. So it might have different physics at a small scale than a big scale. Like quantum mechanics, for example, would be one example of that. Whereas if we look at something at a big enough scale, we don't really care about all the internal quantum mechanics that are going on. But if we look at it at small enough, those are going to have a big impact on the behavior of the system. All right, so there's two quantities that basically are the cornerstones of thermodynamics, which is this lens of physics that we're looking through. Before I go on, does anyone have any comments or questions about the systems intro? Cool, okay. So there's two quantities that are in thermodynamics that basically I'm claiming, as many mainstream physicists also claim, that these quantities basically govern everything that is understood in physics. But they're also some of the least understood things, both by physicists and by daily people. Two important quantities. Who can name one of these quantities?
Entropy.
Entropy, yes. Entropy, which we call a big S. And what's the other one?
Enthalpy.
No. Sorry. Although, yes, it's also important, but it's like kind of derivative of this and the energy. No. You're right on track with the E's, though. Hey, Palana.
Hi.
Welcome.
Thank you. This is Bria.
Hey, Bria. I'm Elliot. Thanks for coming. Feel free to get some food.
Wow.
And we got a bunch of squishy things over here if you want to
Cool.
sit on them
No, I
or
brought a
cuddle them.
Thank you.
Okay, so we're looking we're just introducing the two main quantities of thermodynamics, which are kind of the lens that we're going to be looking through for most of this workshop, so you didn't really miss very much. You've probably been going at it for like 15 minutes. So we have energy, or no, I just gave it away. The other one is energy. Energy. Okay, so energy is defined by a big E, which is why entropy gets this S, because then otherwise we'd have two E's and that would be very confusing. So who can define entropy? What is this quantity, this mysterious entropy? The opposite of movement. Okay. Folding in.
It's like a tendency towards disorganization or disorder.
A tendency towards disorder.
Dissipation.
Dissipation.
Energy loss.
Energy loss. Okay. Anything else? So we have closing in on itself. That would be like low entropy. If something is like not moving at all, then it would have low entropy. Disorder is certainly one way of looking at entropy, and that's how it's most commonly understood. But it's not kind of the end of the story. There's a more fundamental way of looking at entropy that, in my view, is super insightful, that we're going to get to in a second. How about energy? What is energy? What's that?
Everything.
Everything.
The
Indeed.
ability to change.
The ability to change. Okay,
Or-
someone has taken physics 1. Yes. Okay, so energy is, basically the capacity you have to change or to change something else. And Bria, is that right? And as Bria was saying, it's pretty much everything. So matter has energy in it. Light is a form of energy. Heat is a form of energy, like motion is a form of energy. There's lots of different forms of energy we're going to get into. Capacity you have to change. But they all come down to this basic understanding of the ability for you to exert something onto your surroundings. And so when energy changes places, that's how things change. So if I give my energy away, that's what's going to be like the engine of things kind of evolving over time. Entropy, similar to disorder, but not the same as disorder, is the number of ways a system's components can be arranged. So let's take the example of like a dissipating gas as a first pass at entropy. If I have a container and it's totally closed and it has a wall and a bunch of gas over here, and I take this wall away, this gas is going to do what? It's going to expand. It's going to fill in this area over here. So that one moves over here, this one moves over here, and eventually it becomes like kind of spread out within that box, right? So the reason that happens is because there's more ways for these molecules to be arranged in a larger area than there is in a smaller area. So the entropy increase is just saying that another thing about entropy, it always, for the universe as a whole, it's increasing. That's why we say things are becoming like more and more disordered over time. So the number of ways that we can arrange these gas molecules is going to increase over time. So when we remove that barrier, they're going to take this space over here, and now they can be located anywhere within that box. So there's more ways of them to like exist in the space that they inhabit. Another, maybe more intuitive way of understanding entropy is through dice rolling. So let's say I have 2 dice. Okay, outcome. I'm gonna put I want to define 2. Sorry, I'm kind of jumping around here, but I want to define two terms before going to this dice example. One is the macro state, and one is the micro state. So the macro state is the overall configuration of the system. And it can be like a binary thing. So for example, one microstate could be something as alive, and another macrostate could be something as dead. In our gas example, one macrostate could be the gas is all on one side, and another macrostate could be the gas fills up the entire container. Those are two different like overall qualities of the gas in that system. And the microstate is just where every specific component is within it. So that would be where each gas molecule is actually positioned in space within that box, where every element actually is. So in the case that we roll 2 dice, we're going to say that the macrostate is the total roll. So it's the sum of the 2 numbers. The microstate would be the individual outcome of each die involved. And we can use entropy to explain the most likely outcome of rolling 2 dice, which is what?
7.
7. So why, Braden, in your words, would you say 7 is the most likely?
It's the most numbers add up to it, and because I played too many games of 7.
Yes, but the first thing that you said is that the most numbers add up to it. It has the highest number of microstates. So the macrostate of a 7, you could get a 1 and a 6, that would be 1 microstate. You could get a 2 and a 5, that would be a second microstate. A 3 and a 4, that would be a third one, and so on. Whereas what's the least likely roll?
1 or 2.
2 or 12.
2 or 12, right? How come?
Because there's only one possibility of how to get there.
Right, there's only one way. So that macrostate has one lonely microstate within it. So the reason that 7 is the most likely, and it's just kind of like, I'm gonna just draw lines here. 7 is the peak and everything on the edges is lower, is because there's the most number of microstates that give you a 7. So in general, the macrostate that is most likely to exist in the world is the one that has the greatest number of microstates within it. So going back to our gas example, I'll erase this over here. If we have, again, this box, and we say one macrostate is all the gas on one side. So this is what it would be like right after we open, the split second that we open the container, all the gas is over here. There's a certain number of places that each gas molecule can be, and that number, if we were to combine all the possibilities for all the gas molecules, would be the number of microstates that this could have. But when we open up the other side, there's basically twice as many microstates because there's twice as much physical space that those molecules can be found within. Any questions? Thoughts?
Would it be multiplied directly by 2, or I don't know, there's more ways to arrange it in a bigger space than just...
So I would view that each gas molecule has twice as many options now. So total, there's twice as many options for the entire thing. But I don't know if that's actually right.
Well, in 3D, it wouldn't be.
Right, in 3D, it would be maybe different. Yeah, I'm not sure. But the point is that there's more. There's more when you open the box. And obviously, there'd be way more if you open the box way up. And if you open the box to the entire universe around it, eventually none of those gas molecules would be inside anymore because there's way more space for them to fill up. So the amount of space that something can occupy is a very simple measure of its entropy. The more space that is accessible to something, the more entropy it has. So that's why gases, for example, compared to solids, have high entropy, because the gas can go anywhere, where the solid is stuck in one certain place. Okay, so I already mentioned entropy. I said this in words. What's this triangle? Delta, what's it mean? Change. So the change in entropy is greater than 0 for the universe, I'll just say. for universe. So this just means that the number of microstates available to all the things that are within the universe is increasing over time. There's more options for the things that are in the universe now than there were 5 minutes or 5 seconds or like 0.1 seconds ago. Energy also has some behavior that in terms of how it changes. So what happens when I leave my hot coffee on my desk while I go do yoga?
It's cold.
Why?
Because the heat molecules are leaving into the big airspace.
Right, the heat is leaving my coffee into the room. So the coffee is like warming up the air in the room.
Unless your coffee is in a tiny sealed box.
Right, if it's isolated,
Well,
which,
come with a little bit of insulation.
yeah, if the more isolated I make it, the less that will happen, but it's impossible to actually isolate something totally. So eventually, even if it was like a really nice like vacuum sealed mug, it would still end up getting cold.
Is that considered osmosis?
You could consider it like a form of osmosis in that it's like diffusion of heat, but osmosis normally refers to things moving within water.
Okay.
Yeah, so if I have a bunch of salty water and a bunch of fresh water, the movement of the salt into the fresh water would be called osmosis. So what, I don't know, just energy dissipation is what I would call it, or thermal equilibrium. So thermal equilibrium is the notion that all the temperatures want to be even. So the fundamental behavior of energy is that it hates gradients. It hates when things have different levels of energy or different capacity. So are people familiar with the phrase nature abhors a vacuum? That is one consequence of that. Then also that phrase encompasses both energy and entropy. But one consequence of that is that if there's no energy someplace, something that has higher energy is going to fill that void. And so there's going to end up with a smoothing of the amount of energy that things have. So a consequence of that we might see outside is erosion. At the top of a mountain, the particle has higher energy than what's at the bottom of the mountain. It has a potential energy. It can roll down the mountain. And so over time, the smoothing of the mountains, the erosion that's happening, is because energy wants to be smooth. It doesn't want there to be big differences in energy. And how that happens is by things that have high energy transferring their energy to things that have lower energy. So that's why I would say delta E is less than 0. Things have a tendency to give up their energy. They want to lose energy. So together, these two things, these two properties, the increase of the number of microstates or possibilities that something has, and its tendency to want to release its energy, these are fundamentally at odds with one another. And it's their interplay that kind of dictates, in my mind, pretty much everything from our social interactions and our social lives to material physics. Does anyone notice right off the bat why these two tendencies are at odds with one another?
They're inverse.
How?
So the change for energy goes, it wants to give up that energy, whereas the change in entropy wants to take it. So you have to have, for all of the energy that's going to be released from the energetic energy, all of that's going to get sucked up by the entropy state. And so you can never have like energy go towards sucking up the energy. You can't do what the other one does in some inverse.
Right. So one of the things, the nuggets that stuck out to me from what you were saying is that when something releases its energy, that's transferred to entropy. That's an increase in entropy. So unlike energy though, entropy doesn't need to take it from anywhere else. So in the case of like the box example where I moved the thing, I didn't have to take entropy from anything in order for those gas molecules to gain entropy. So entropy is not conserved in the universe, it's increasing, whereas energy is. Energy is always transferred between things. But what you're saying about when energy is released, that corresponds to an increase in entropy, is right on the money. So the reason why that's problematic is because energy, when something has higher energy, it has more microstates. It has more ways of it, it has more possibilities for how it can be arranged. So let's consider every physicist's favorite example, which is a ball in a little U thing. So this ball is just going up and down this ramp. And how high it can go in the ramp, we're going to assume that there's no friction. It's going to keep oscillating back and forth forever. Its height basically its maximum height corresponds to its energy. So if it has more energy, it can climb higher up the ramp. And it'll be going faster at the bottom, the higher it starts. Does that make sense? So if it has lower energy, it also can only be found along this line. So compared to this ball, which has a higher energy, higher E, higher energy, this one's lower E. This ball also has this section and this section. So since its entropy is correlated with the space that it can inhabit, this ball has higher entropy as well. You can find it in more different places within this ramp. There's more ways that you can arrange this ball within the ramp. But what happens when things have higher energy is they want to get rid of their energy. They want to give their energy to something else. But by doing that, they also lose entropy. But if this ball has lower energy, let's say it has friction with the ramp, it has lower energy because it's got friction and slowly slowing down. By the time it's here, it also has lower entropy. So that's the conflict between energy and entropy, is that energy wants to be released, but energy is also what gives you possibility, and your possibilities want to increase. Does this make sense? Okay, so ultimately, what will happen depends on what the energy does for you versus what the energy does for your surroundings. So in the case of friction, the way that this ball will lose energy and entropy by friction, by slowly going back down to here, is if its energy creates more possibilities for the molecules in the ramp that are taking that energy than it did for the ball. So if the increase in entropy that something else would have by having its energy is larger than the entropy that it gets from that energy, then it's going to release it. We'll get into that in more depth. So there's an equation for this. I said at the beginning, there's one equation that pretty much all of physics is derived from. That's this one. It's called the Gibbs free energy equation. So this delta G is called the Gibbs free energy. And this is our energy and our entropy. And basically, delta G wants to be less than 0. So that can happen if the change in energy is less than 0, which is what it wants to do, or if the change in entropy is greater than 0, which is what it wants to do. And so there's 4 different cases for how delta E and delta S can be for something that determine how something is going to end up behaving. We can have both of these be positive, we could have both of them be negative, or we could have one positive and one negative and the other positive and the other negative. So I'm going to make a table for all those options that should hopefully make clear what I was saying just a minute ago about how I will give up my energy if it creates more entropy for something else. And then, of course, we have this T. Who wants to guess what this T is for? It's hanging out in there. We haven't talked about it. Time? No. This is temperature. Temperature of the surroundings. So these delta E and delta S would be for the object that we're interested in, or for the system that we're interested in. And the T is for the surroundings that it has. Okay, so we have 4 possibilities. We got, we'll make this table, delta E, delta S, delta G, and then, so delta G wants to be negative. When delta G is negative, then what that tells us is whatever behavior this describes is going to spontaneously happen, or it's going to be most likely to happen. Now, things operate kind of probabilistically. So it's not that just because delta G is less than 0 that thing's going to like immediately spontaneously happen. What it means is that over a long enough time period, the most likely outcome is whatever behavior in terms of the energy and entropy change is what's going to end up happening. So I'll make a column right here for spontaneity, and then examples, because I'm running out of room. Okay. So we could have delta E negative and delta S positive. We could have the opposite, positive, negative. We could have positive, positive, or we could have negative, negative. Okay. So let's look at this first case first. So in this case, we're releasing energy. That's what delta E is negative, means we're giving up our energy. We have less than we started with. And our entropy is increasing. So what will just the sign plus or minus of delta G be in this first case? I heard something. Negative. Because we have a negative number right here, and then minus a positive number, so that's also a negative number. So each of these is always going to be negative, which means this whole thing is always going to be negative. So is this going to be spontaneous? Yes, it will. Okay, now what's a physical example of something like this? So an example of something that is both releasing energy, but also increasing its possibilities or increasing its arrangements. Anyone think? A car. How come?
So you're releasing the energy of the combustion, but you're also increasing your possibilities by going from an inert state to being able to move.
Absolutely. So combustion, that was the one I was looking for. A car is a great example of that. And not only does it give your car more possibilities, and that now your car can be found over there because you use the energy from the gas to move your car around, but it also gave the gasoline itself more possibilities because the gasoline went from being a liquid to being a gas. So in that transformation, it now has way more arrangements. So what happens in a combustion is that we have a lot of stored chemical energy and like a really long carbon chain, a bunch of atoms that are tightly bound to each other in a really long chain, and we've sliced it up and turned it into carbon dioxide and methane and all these other carbon gases that can then go into the atmosphere. And by doing that, they lose the energy that they had stored in the bonds in the molecule, but they now also have more freedom to go wherever into the atmosphere.
And become whatever as well.
And to become new things, exactly. They're not trapped in that gasoline anymore. How about an example from like your personal life? Is there any moment that you can think of where you feel like you released mental energy and gained mental possibilities?
Studying?
Hmm?
Studying?
Studying, that could be one. How come?
Well, you use your mental energy to get information, and with more information, you can make more choices.
Yeah.
When you tell people that you work with, what your expectations of them are.
Okay. Elaborate.
Well, having a meeting
Right.
with people that report to you, and you're
Right.
expending the energy of sharing a vision for what you want to see them accomplish.
Right.
And now that energy has been shared with 10 other people.
Right. And now there's more possibility
There's more
for what that team
possibility.
can accomplish.
Yes.
So like taking the skeleton out of the closet, right? The skeleton was in the closet, and now you take it out and you can like look at it on the table and like put all the pieces in different places.
Yes. Exactly like that.
So the example I always go to, just because I think it's cute, is a first kiss. A first kiss. So a first kiss, who here has had one? What's it like?
Exciting.
Why? What's happening in your mind?
Everything.
Creating
Right.
telling your whole future story.
Yeah. And what happened maybe like 5 minutes before? What was in your mind?
Wait, did you know about the kiss? Was it?
No, you didn't know.
Oh well, then you had no idea. There was no knowledge of the fact that you were
Let's say you wanted it to happen.
Anticipation.
Anticipation, right? You've got like this mental energy built up in the form of anticipation. You release that energy, and now you've opened up more possibilities for what that relationship can be like. So now you've opened up a whole new type of relationship with that person. So you've increased the amount of possibilities while releasing that anticipation that you had built up. So when we talk about all these mental examples, it's totally okay if we disagree. You know, each of our own mental experiences is going to be different, and we're not going to think of the same experiences in the same way. And obviously, there's also not like one singular mental experience. So we're going to talk about like different mental states like curiosity, desire, attachment, love, and things like this later on. And obviously, we're all free to experience those things in our own way, and we're also free to combine them with other types of experiences. So they're not as binary, whereas combustion, pretty much, this is what it is. Okay, what is the sign of delta G in this next case? Both of these are flipped. Negative? Positive. Yeah, it's always positive, which means it is unlikely to be spontaneous or not for long. But still, we find lots of examples of this in both the physical and social realms. What would be an example of this happening in a physical realm where we are accumulating energy and decreasing possibility?
Freezing water.
Freezing water, close, but no, actually. But hold that in your mind.
Hoarding wealth.
Hoarding wealth. I like that one. That's a great social example. So why would you put that in here?
Because the more people hold on to that money or energy, then the less of it can sit.
Right. And does it open up, if you have $1 billion and you get another $1 million, how much possibility does that open for you? Not much. Whereas if you took that same $1 million and distributed it amongst, let's say, 1,000 people, 1,000 average people, how much possibility would it open up for those 1,000 people who each got $1,000? Lots, right? So that's what I was talking about when I was saying how energy will be transferred and released when it gives something else more entropy. So we'll get into that a little bit later. How about something in the physical world that is this? Yeah.
Like jamming a river and like using it to generate electricity.
Jamming a
increasing
river?
The velocity of the water.
Well,
Yeah,
not
totally.
necessarily. You're just kind of changing the state at that point in time, because if you're taking like the water for sure, like but you're also taking the possibility of that water and turning it into electricity, and that electricity could give more potential for all of the people that can use it than all of the things that it could have given with the river. So that's I could see how that would work, but there's also a possibility that actually might not.
And it's like a loss of energy because like it's not 100% efficient.
Right.
Well, yeah, that's it.
Yeah.
So what about just jamming a river and not using it for energy?
Right.
Yeah.
Yeah, it depends on everything. Like depends on the sequence of steps that you take. So there might be one step that looks one way and another step that looks a different way. Maybe damming the river is one, but then generating electricity from it could be this one.
Yeah.
You know, so you're kind of taking advantage of these dynamics when you do something like dam a river.
Playing a sport.
Playing a sport, how come?
You're taking the collective efforts of all of the community and you're condensing it down to this team is really the team that really knows how to play that sport.
Yeah, totally. You're putting a lot of energy into it also. You know, we build these huge stadiums, people drive for miles. We have a huge accumulation of energy for something that has relatively few outcomes, right?
Except
Right.
for like good feelings.
Right. Another one, I'm gonna put photosynthesis up here. Photosynthesis, that's my favorite. So a plant is doing the opposite of the combustion, doing the opposite of the fire. It's taking the energy from the sun and hoarding it, and in so doing, trapping gases and turning them into solids. So photosynthesis. Okay, next up we have energy increase and entropy increase. What might this delta G look like?
Could it be either?
Could be either. Yes. What does it depend on?
It depends on whether or not the change in energy is greater than the change in temperature, or than the temperature times the
Right. Yeah. So it depends on relatively how big these are, and also on this temperature. So it depends on T. So it'll be negative when temperature is high. So when something around you, when your environment is really hot or your environment is really high energy, you're going to take some of that energy yourself. That's why this delta E is positive, and that's going to give you more possibilities than it gave the ambient stuff that had the energy in the first place. Do you have something, Ryan? No. Okay. What are some, spontaneous. So again, this depends on, that depends on T should be in this box. Okay, what are some examples of this one? Energy being hoarded by something, and it's increasing that thing's possibilities. Mom, come back to us with your water stuff. You said something earlier that
Ice, I said.
you said ice. Okay, so is ice hoarding energy? It's the ice is down here. So what was this D1? Boiling or melting. Melting. What were you gonna say, Ryan?
Like the phenomenon, if you're like a certain level of wealth, you'll never not be wealthy again, because once you get to a certain level of wealth, it's like becomes far easier to like make more wealth.
Right.
Or at some point in time, it just generates wealth on top of wealth.
Right. Yeah, you get like a feedback loop where your wealth gives you more and more wealth. Although I would maybe argue that that's not increasing your entropy. That once you have a bunch of money, getting more money does not give you more possibilities. And in fact, oftentimes I would say it gives you less possibilities, because someone probably is spending a lot of time thinking about their money and thinking about ways to make money. And so their thoughts in terms of what they can do with their life have been limited by that attachment to money that led them to get so much money in the first place. That's my perspective. Maybe Bill Gates would see it differently.
Yeah, Bill Gates would say he could go out and save the world from HIV.
Okay, well, then why does he still have $100 billion? I don't know. Bill Gates and I can talk another time. Okay. How about this one down here? Wait. How about a mental example of this? Or like a social example? I guess we have the money thing already, but what's another social example?
So hoarding energy and then creating more possibilities, so creating more entropy with that.
Conception.
How so?
It's energy coming together that then creates new outcome.
Yeah. I would say just like reproduction in general falls along this life, or life kind of. I mean, life does all of these things.
But wouldn't the actual like act of birth be like releasing energy? In like a sense, it would be releasing energy for like the person who's holding the child, right? But we're gonna be like increasing, I guess, the possibilities for the child that's born.
Right. Yeah. This is where these things become very, very complicated, because you have a lot of pieces that are all being affected differently. So maybe like the mom has one row, and the baby has another row, and the doctor has a row, and the air in the room has a row. You know, all these things are related and part of that system. So it gets pretty messy.
So with the relationship then, could you build kind of like a table for each piece that's involved?
Yeah.
And then define all of the changes, and they could even be contradictory from one piece to the other.
Yes.
Yeah, that's what makes the system actually.
Right. Absolutely. Because the change in energy and the entropy both, there's not just one type of energy or one type of microstates that something can have. So for example, mentally, or like me as a self, I might have mental energy that is associated with like in a very immaterial way. And then I have physical energy, which is my body, and there's like all these different types of energy. And with the entropy, it's the same way. Physical space is one way to define the entropy, but like we saw with the dice example, that had nothing to do with physical space, it's about information. So information arrangements can be a type of entropy. So there's lots of different subcategories underneath each one of these. And if we were to like somehow add them all together, then that's when these tables are useful. So we have melting, conception. I would say wealth redistribution, that's one we talked about. Wealth redistribution would fall in this category. And we said this will happen when the temperature is sufficiently high for your surroundings So what that would mean in the wealth distribution context is just if the difference between the amount of money I have and the amount of money that someone else has is large enough, that divide is going to break. And so when we have this massive inequalities in terms of how much money or that type of energy that people have, once that divide gets big enough and that gradient gets big enough, then it will break. So when the temperature outside of me is so much higher than I am, then I will find a way to get that temperature. All right.
Can I ask, like, how does temperature like relate to like that social example? So what is actual, like, what are you saying is the temperature in the social instance?
Yeah, that's a very interesting question. I would say it's like that energy of the, it's like social energy, or it could be informational energy. So a mental example that I would put in this category is curiosity. So I would say when I'm curious about something, I'm accumulating mental energy about that thing. And that's increasing the possibilities that I have, because as I learn about that thing, I'm able to use that knowledge to do things that I previously wouldn't have been able to do. And I can be curious about something if the outside temperature is higher than me. So like I can't be curious about something if I already know more than is possible to know. But I can be curious about something if there's like a wealth of information out there that temperature of information is high outside of me, and my temperature of that information is low, then I can be curious about it. So if I feel like I have a lot to learn, then I can be curious about something. I'm not going to be curious about something if I feel like I can't learn anything about it. Does that make sense?
The temperature is the gradient.
Yeah. So temperature is the energy gradient.
So it's like the higher temperature, the more energy it has, the lower temperature, something that has less energy.
Right. Exactly.
Like in the example of wealth redistribution, for example, the more people who know that they could have that wealth versus the less amount of people that know they could have the wealth, that's your energy distribution rate. So the more people who know that they could have that wealth but they're being kept from it are going to increase the temperature of the wealth distribution inequality, which is then going to break the gradient eventually, and that's when you see like riots or whatever come from the systems of that.
Totally. Okay. We're going to finish this one, this last row. We're going to return to this in the second part. So after we finish this, I'll have like a 10 or 15 minute next section, and then we're going to break so that people can eat some food and like stretch your legs, go to the bathroom, whatever. All right. So this last row, we've already hinted on this. Again, it's plus or minus, and it depends on T. So this happens when T is low. So basically, these two are like opposites of one another. This would be what's happening to, in the same example that we've been using, this is what's happening to the super wealthy person, and this is what's happening to everybody else in the wealth redistribution case. This is also freezing. So something is, when something freezes, it actually releases energy. So that might be kind of hard to wrap your head around, but if I am freezing, I've had some energy in liquid form, and I now am solid. So I've released energy, and I've also released my entropy. And of course, that happens when it's cold. And the temperature outside of me is low, and it will take my energy freely. Does this make sense? Cool. So we're going to return to this and get way more in depth and like more social and mental examples. But first, I want to talk about some of what I find, or what for me have been some of the most compelling and interesting insights from this equation. And it has to do with that metaphysics stuff that we were talking about earlier. So in my view, the goal of advancing physics or knowledge should be to include more and more things into your framework, right? So if something doesn't explain something that is obvious, then it obviously can't be the whole picture. So for example, right now, in the physics community as it exists right now, consciousness is not an issue that's talked about. But it's obvious to me that consciousness is real and that it deserves attention from science and from physics. So that's part of my motivation for like embarking on this whole quest, is to try to explain some of those things. Like, why is it that consciousness exists? What is consciousness? And also, what is life? So this section is going to be titled Origins of Life, Consciousness, and Gaia, which is like the living earth. The idea that the earth is kind of viewed as one, can be viewed as one single organism. So we're going to examine life, consciousness, and kind of the earth as a whole from this framework of Gibbs free energy and thermodynamics. So let's first tackle life. It's the easiest. So let's imagine Earth without life. Does anyone know what the equilibrium temperature or the average temperature on Earth would be if there was no life?
I imagine much hotter.
Much hotter. Why?
Will there be like nothing really to keep out a lot of the radiation from the sun? The heat would then, I mean, there's nothing trapping it either because there's no greenhouse gases, but it's just like, it's like having no protection from that heat, so there's no dissipation or anything.
Okay.
I mean,
Is there
life
any
is in
disagreement?
humans or life is
All life.
It was like a Mars type of planet.
Yeah.
No oxygen.
Right. If it was just in doing whatever it would be doing without life.
Can we use Mars as an example?
Sure. Is Mars hotter or colder?
I don't know, but I'm just wondering if that's the equal.
Yeah. I mean, it's not equal because Mars is also a different distance away. It's further away. But Mars is way cold. Like, Mars has ice caps made of carbon dioxide, like dry ice caps. There's also water. But it's so cold that at the poles, carbon dioxide is a solid. So it's way cold. On the Earth, the average temperature, average T, would be about 0 degrees Fahrenheit. Does anyone know what the average temperature of the Earth is? Just roughly,
Today,
you have to guess. What?
no,
Is it the same as a human?
With life? No, it is not. The average temperature is 58 degrees on the surface of the Earth right now. So it's much hotter than it would be otherwise. So viewing these in terms of like a form of energy that the Earth has, the Earth is hotter, it has more energy. And viewing the difference, the outside thing that we're getting the energy from is the sun, right? So earlier we went through how energy wants to decrease and it wants to smooth out gradients. So steep mountain will become flat. We can view the sun as like the peak of the mountain and the Earth as the bottom. With life, the Earth and the sun have closer to the same temperature than they would otherwise. So photosynthesis, for example, is capturing energy from the sun and not letting it leave. So the Earth is increasing its energy through the photosynthetic process. So right off the bat, with life, we're going towards a negative delta G here. A negative gives energy. So we're going towards something that is going to happen spontaneously. Of course, the other, so I'm going to just write that. So on Earth, or actually, delta E for the Earth is greater than 0 with life. And that's actually different from what I just said. Because the temperature of the sun is so high that the Earth will take that energy and it will do more stuff, create more possibility with it. So in terms of the entropy, how does it ways, just in terms of how things can physically be arranged on the Earth, are there more ways to arrange things that are alive or not? Like what would the Earth look like if you were on the surface of the Earth? What would you see if there was no life? Rocks. Okay.
Ice.
Rocks and ice. So it'd be kind of like everything would be like at surface level, right? Maybe there'd be mountains and volcanoes and stuff too. But for the most part, all like the physical material of the Earth would be at surface level. With life, what do we see?
Well, it's everywhere.
Yeah, it's everywhere. It's in the sky.
Underground.
It's underground. It's underwater. So life is taking materials from the Earth and spreading them out. It's creating more ways that you can arrange things. So while my physical body might have less ways that it can be arranged in me than if I turn myself into a gas. So I'm lower entropy than I would be as a gas. I compensate for that in the amount of possibilities that I create in my surroundings. So for example, oil trapped underneath the ground, we take that oil out of the ground, we put it into the atmosphere. Huge increase in entropy just from that. Then what we do is we build spaceships and we send them outside of the solar system. So we take physical material, rocks, that had very little possibilities on Earth, and we turn them into something that can now be found like out in the galaxy, like anywhere. So we take the material, namely rocks and crystals and other things that are very low entropy, and we turn them, we smear them out. You know, we find bacteria in the sky, we find birds flying. All this is increasing the number of ways that the material constituents can be arranged. So a living Earth has more entropy than a non-living Earth because of it's basically mining, you know, and microbes at the very beginning were mining the surface of rocks and taking those minerals and taking those crystals and putting them into liquids and putting them into the atmosphere. So life is essentially an engine of entropy. So while I myself have low entropy compared to what I would have if I was a gas, when I eat food or when I drive a car or do any of the other things that humans do, I'm creating a huge amount of entropy in my surroundings. So I'm taking like food that is like low entropy, and I'm turning it into heat, and I'm turning it into gases when I breathe out carbon dioxide and all this stuff. So entropy goes up with life. And this is one of the things that a lot of people I think misunderstand the most about energy or about entropy. People think that it goes against entropy because they see life as ordered, and ordered means no entropy, but that's not the end of the story. Life is creating more possibilities overall, even though we do have an ordered structure. Okie dokie. So next is consciousness. So here implicitly we're talking about kind of two macro states, the macro state of no life and the macro state of life. And for the consciousness discussion, we're going to be talking about two macro states again. So macro state 1, no consciousness. Macro state 1, unconscious. And macro state 2, conscious. So the one of these that is most likely to happen is the one that has the most number of microstates, so the most number of ways that things could be arranged within them. So does anyone want to think about which of these which has more ways of arranging? First thought. Well, you said it's gotta be. Why?
Well, because with unconsciousness, there's nothing to arrange. There's no thought. There's nothing. Yeah. So with consciousness, you have something versus unconsciousness.
Right. Okay. Anyone have anything to add to that? Okay. So.
I think it would depend on like your view of unconscious and conscious too.
How?
So if you like view unconscious, like the unconscious collective, as there being like information that's like floating out there, then there is stuff out there. It's just not like contained.
Okay. I think I might see what you're saying.
It's like the iceberg method, where what's above the water is consciousness, and what's underneath the water is unconscious
Right.
or subconscious.
Okay, yeah, subconscious, which maybe is different than unconscious.
Yeah.
I would say.
I would hope so. That's a little different.
So this all hinges basically on one thing, which is there a one-to-one correlation between a physical state and a mental state or not? Because if there's a one-to-one correlation, then these would have the same number of microstates. Because a physical state that's tied directly to a mental state, those are now equivalent states if there's a one-to-one correspondence. So you don't increase your entropy by having consciousness if there's an exact one-to-one correspondence. But if there's not an exact one-to-one correspondence and consciousness has its own arrangements, as we were talking about at the beginning, that it just like first there was nothing and then there was something, that those conscious states actually have lives of their own apart from the physical states that maybe they're like tied intimately to, then there'd be more microstates in the conscious universe. So ultimately, the number of macrostates between these two hinges on macrostates. Hinges on whether there's a one-to-one correspondence. One-to-one correspondence.
Can I clarify something?
Yeah.
So does that mean like when you have a new idea, if there was a one-to-one correspondence, that would mean like there's a certain molecular and energetic arrangement in your brain that always corresponds to any given mental state?
Right. Yeah.
And then to say that's false is when you have a new idea, then you could have the exact same like physical configuration of your brain while you're having that idea.
Right. Exactly. So if like one physical configuration of your brain / body and environment can lead to two different experiences, then there would not be a one-to-one correspondence. Exactly. So I find this all very interesting, but I also, this is when I get into the realm of like armchair philosophizing and ultimately not caring because the universe is conscious. It's like, okay, it's obvious if the universe is conscious, then somehow the entropy in the conscious universe is probably higher than the unconscious universe, and I can observe that just by being conscious. I don't need to like pick it apart too much, but it's still interesting. And later on, we'll talk about different macro states within the conscious universe. So now that we all understand that the universe is conscious, we can take one macro state, which is like love or fear, or love, and another one that's fear, and then compare the number of micro states that each of them has. And it's that's like I find much more interesting than this.
Well, it's like a quantum state too, because you can be both loving and fearful at the very same time.
Yeah.
So you have 1 and 0, and then 1 1 and 0 0. Like it's
right.
Yeah.
Yeah, that's where a lot of the mental analysis gets very tricky because really we are always a superposition of mental states. Maybe not always, but most of the time we have lots of different stuff going on here, and it's not like we can define it, say like, oh, I'm like just afraid right now, and that's the core of my experience. I mean, certainly I've had experiences where I felt like I was like just loving or just like terrified, but they're more rare, I would say. Okay. Cool. How are people feeling? Should we take a break? This was my break. We don't have to take a break. Okay. Stand up and stretch.
Yeah.
Break time. Okay. We'll start again when everyone looks ready.
Wow, Elliot, this is so fresh.
Thank you. Thanks for coming. Yeah, get some food. I'm sure there's lots of beans left. I should probably get some food. Let's see if. Nice. Yeah, straight upstairs, just like straight through the cloth. Just keep going. Dang. People are watching this video.
What
I'm live
Oh,
streaming
you
it
are?
on Facebook. Yeah. Your sister was watching. Yeah. My sister.
Which one?
Linda.
Yeah, we do. That's my figure out this.
Yeah. Yeah.
Just because I'm ready to do it.
Yeah.
Dude, it's so good.
It hasn't been.
Integrations.
I'm glad you still think
So I'm interested.
Well, I didn't think so, but like
I think this place is
a lot of every day.
Is it?
I believe so.
I was about to say, because it doesn't seem like it has any 1 or 2 type of personalities dominating the space.
Oh. Okay, sure.
I think in the second place, plus the Matthew questions.
I can see it.
Oh yeah. Like,
Crystals.
sounded like you.
You know,
Point when you
Taking
ate it.
it all over.
there's a potato or a lemon.
Oh yeah. Wrapping up.
We're moving the floor on.
Either way, it's awesome.
Yeah, I'm amazed every time. No.
And then the summer is all of that. Did you notice that? Yeah.
Being within a very conservative space for about 4.5 years.
That'll do it.
Yeah. I didn't really get into it myself. For myself, so I didn't really follow up on it.
Okay, sweet.
That was another one. Motivation. Yeah. The military doesn't typically look on those types of ways of thought as
But
viable.
anything at this point when you're making the transition over to the other.
Well, that's good.
Oh,
Went to the military for 4 years.
yeah, they seem to.
Like the first time, so he got his scholarship for it, and then now he's that's like so awesome. The military is like entirely paying for that.
That is fantastic.
Yeah.
I think that should happen more often. Especially with how much we spend on the military industrial complex.
Where you go?
Especially how much we spend on it.
Yeah. Elliot's energy. Is that what's happening?
I hope so.
What's happening?
Braden's moving to Florida because my mental energy is. Something about entropy. This is definitely the reason, one way or another.
We're in Florida.
Orlando,
Alright.
What are you guys doing there?
same thing.
Same thing.
Trying to take over the world.
Yep.
Same thing we do every day.
Yep.
I'm gonna take out.
We're increasing our possibilities
Right?
by taking up more spaces.
Right now.
It's so terrific. I did a workshop this past weekend about reprogramming your subconscious mind. So I have
Oh, that's cool.
subconscious, unconscious, and conscious all in the 4-day period.
Blue, we were talking about reprogramming the body, the water in your body.
Mm-hmm. Masari Moto, who's Lipton. Yeah. Love. Love him so much.
It was really interesting because the person I was talking to was saying that it's actually impossible to be in the fear vibration and the love vibration at the same time.
Mm-hmm.
And I just think of the perspective like, wow, it's actually making a difference on how you think.
Mm-hmm. I love that. What's your name?
Hi.
Tyler and Bria. Yeah, nice to meet you.
This is so fun. Thanks, everyone.
Thank you. Oh no, I mean actually.
What, Ryan?
Could you say that thing again where you said, I don't really care whether or not there's actually more entropy with conscious beings because we are in a universe that has consciousness, and therefore.
Right. I was saying it's easy. I was trying to determine whether or not consciousness is likely to happen based on whether or not it increases entropy or it doesn't increase entropy. And I think that it increases entropy because I don't think there's a one-to-one correspondence. That's my personal view.
And why do you not think there's a one-to-one correspondence?
I just think there's a lot of outlandish stuff that happens like between the interactions of consciousness and the material world. Like there's things that we have no explanation for how materials could be arranged based on well-known physics. That seems like consciousness is like an external force that's changing the physical world. So for example, like very simple to understand one is the feeling that you're being stared at. They've done studies where you can tell that you're being stared at, like better than average. Not perfectly well, obviously, but better than average. And I just don't see how there'd be a physical like reaction happening that would lead you to that belief, because you're not taking in light from them, which is how you would know. I mean, maybe it has something to do with like our electric and magnetic fields in our brains, Like certainly there's a lot of stuff that we don't understand in terms of how our brains interact with the physical world. However, I would say that it seems like consciousness can do things to the physical world that aren't explained by anything else other than consciousness. Or like energy healing would be another one, or like miracles, or people levitating. Like this is all stuff that I believe happens. Like I've seen the accumulation of evidence.
You've shown it in physics too, that consciousness locks molecules, I don't know, quantum particles in place.
Yeah,
I
looking at
mean, the observation
Right.
itself changes
Right.
the physical.
Right. That our consciousness can affect material things in a way that material things don't affect each other. That's basically what makes me think it's outside.
Experience.
Yeah. Or like remembering past lives, or like being able to like, what do they call it? Remote visioning, where someone like the army military used to hire people to spy on the Russians because they were psychic. You know, there's no like physical explanation for it other than consciousness has a life of its own that is not currently encompassed in our understanding of the physical world.
I think I'm sold. All your
Yeah, and there also is too, like airplanes, for example, they didn't exist, and consciousness was basically the thing that created those things, or gave the more possibilities for those molecules to be arranged like that. Versus in nature, that would most likely be very unlikely as a spontaneous act for a plane to just like.
Right.
And then whenever a physical action happens with the person, do you have just one thought, or do you have multiple thoughts on that? Like, oh, that person just greeted me with a smile. That must mean they either like me, or they think I'm funny, or like whatever thoughts you have a million different thoughts from one simple physical interaction, which to me says consciousness is far more than just the physical.
Yeah. Yeah, but ultimately the reason, like, I do care. It's not that I don't care what the answer is. It's just obvious what the answer is. It's obvious that we're conscious.
There's
Well,
nothing
isn't
to
it
be
your job
curious
to
about
prove
because
why
you've
it's
already accumulated that knowledge.
What? No, I have no curiosity because I already have the knowledge. Yeah, maybe that's it. But there are certainly other implications. Like this, the conscious, not conscious macro state is actually independent of the living, non-living one, I would say. So you can ask whether a non-living thing is conscious or not conscious, just the same as you'd ask whether a living thing is conscious or not conscious. So the ramifications that it might have is that non-living things are conscious and that they have consciousness as well. So that's certainly an interesting conclusion, I'd say. Okay. Yeah, but what I find more interesting is what we're about to talk about, which is how different like types of consciousness play in this kind of grid framework. Are people ready? Everyone's here, I think. You ready? Cool. Okay, so I want to just put out some mental states and hear where you think they fall in this grid. We've already talked about a couple of them. What about creativity? The mental state of feeling creative. How would you classify it? Just for yourself, it doesn't have to be like universal, this is what creativity looks like. But for yourself, we say creativity is an accumulation or release of mental energy. Let's do that one first. Right.
I'd say it's an expenditure of energy for an increase in entropy.
Right. Okay, so it would be this one. You're releasing energy and you're increasing entropy. Okay. Could be. Why do you think that? What about your experience as like a creator leads you to think that?
Well, it takes effort, and then what you get more creative in the process, which means you have like there's more you could create.
Okay.
That's more possibilities.
So by creating, you open up more things that you can create or maybe think about, and it takes effort. So it's this. Anyone see creativity falling into a different one of
You know,
these?
I don't know if I do, but I see creativity as certainly increasing entropy. But while I'm reducing energy, it is also enabling me to accumulate energy at the same time. It's like wealth, it builds on itself.
Right. Yeah.
The ball rolls bigger and bigger and faster and faster, the more creativity I am.
I think Scott's almost saying that like an increase in entropy is kind of an increase in energy. It's like when you're talking metaphorically and not like purely physically, then like the line between entropy and energy is kind of blurred sometimes because like more power is like more capacity, which is like in the form of energy.
Right.
I think like the spark of creativity can sometimes feel like it brings with itself energy, but then bringing it to reality is what takes energy.
Yeah.
I would say the same thing.
Yeah, I view this in a very similar way. I think where, like, I would say the spark of creativity is kind of in this one, where I'm like, I feel like when I have a creative breakthrough or insight, it's like a dam has been released, and I've had some release of energy that allows me to think about things in a totally new way. That's the creative insight. And then the work of like, okay, now I have this idea for a book or a painting or a game or whatever. Now I'm gonna have to like accumulate a lot of energy, and it'll also have to reduce my entropy, but then in order for it to be executed, I'm gonna have to reduce my focus on other things. You know, so if you're like focused on like building something, then over time you become attached to that thing and you're unable to like have that entropy again. So
It's interesting though, when you're having a clear thought or any thought in the brain uses so much calories. It's very energy intensive just to have a thought.
And the calories are physical energy.
That's
You know,
physical
it
energy
turns
to have a creative thought. It's a lot of
right.
But then it
physical
becomes
calories.
something invisible. So it's like taking visible food and making it into an invisible thought.
Right. Yeah, that's a very strange
Until it
interplay.
becomes something physical.
When you talk about energy being exchanged in the physical world, we talk about it like being taken from somewhere and given to something else. You know, I take the energy from my food and I turn it into like my ability to move, to think. It's unclear to me if that's true in the conscious realm. If I accumulate mental energy, did I take it from somewhere? Maybe I took it from my food. Maybe I took it from like the ether or something, but it's unclear to me. And I honestly feel like in the physical world, we think that the total energy in the universe does not change. That's all like exchanges between stuff. My kind of intuition experience tells me that maybe that's not the case in conscious energy, and the conscious energy is increasing, and that I can have an increase in conscious energy without having to take it from anywhere. It's like self-generated. But maybe it's being taken from the physical world. It's very unclear.
I think
Maybe
there's
it's being
both.
received.
I think there's both. I mean, I've had energetic vampires in my life before, and you can feel that, but I've also experienced doing energy healing and, you know, receiving energy from a universal light source standpoint, where I think it's both.
Sure. Yeah. No, I think so. And this conscious talk, it's never like one thing. I don't think there's lots of. And also, these like the experience of what it means to create something is going to be different for everyone. Okay, how about attachment? The feeling of being attached to something. Where would you put it in here?
Definitely hoarding.
Hoarding. So one of these two.
Yeah, because you're not letting go. You're continually like just accumulating that feeling of attachment.
Okay. And how does it affect your entropy, your possibilities?
It probably decreases your possibilities.
Okay.
Is the more you're just focusing on that one object of your attention, rather than like all of the objects that you could be focusing on.
Well, because you expand it. If you think of physical representation of like, I'm attached to her, I'm holding on to her. We can't move as fast. We can't change the corners as fast.
Right.
We're going to be slowed down a little bit.
You can't even think as fast because you have to like, which way do we want to go? Well, I want to go left. I want to go right. Well, okay, now we got to figure this out. Yeah, I can see that.
Right. Yeah, totally. So I would kind of view it here also, that I think that physical analogy is great. And it's so interesting to me how a lot of the words that we use to describe physical things and the words we use to describe mental things are the same. And I think that's in part because of their behavior here. Like we say, like a thought condenses maybe, and that we could look at that through this view of like how condensation happens, which is condensations. Releasing energy, maybe this one, condensation. Anyway, okay, so attachment, probably here. how about like love or yeah, let's just do love. How about love? Where would you say you're feeling love with your whole self? What kind of energy is being exchanged or moving, and what possibilities are being created or limited? Plus plus. How come?
Because I feel like being filled with love is like filling with energy, and then it also expands the possibilities of what's possible.
Okay.
Not necessarily too, because like I've definitely felt drained after like loving someone. So it's not necessarily always like it gives you energy either. You could still be expending energy and increasing your possibilities, whereas you're not increasing your energy and expending more possibilities too. I can see how it would work, especially if like the two people are like out of sync and you're like angry with each other. That would like you're still increasing each other's possibilities, because without each other you wouldn't have to deal with the emotional stress, but it's also very draining because it's emotional stress. So
then is that love we're talking about, or is that frustration and anger we're talking about?
it's the
Are those
love.
two different equations?
It's the love, because you like. So who has more power in a relationship? One who cares more, or the one who cares more?
That's a different question.
Right, but it kind of relates to it, because you're still giving energy and taking energy.
No, I see that different. That's more of a codependency. Love in its pure form, I think, is limitless. I don't think there's a limit on it. I don't think you can really lose it.
You can definitely lose love.
Well, you can lose
You
love
can lose
for
the
a
love of
person,
a person toward you.
but that's different. I mean, I look at love is, I mean, it's boundless. I mean, I loved Scott. I had a child. I loved that child so much I thought I could never love anything more. And I couldn't love him. And then you have another child. And then all of a sudden you find that you can love something, you can love more. I just think there is no limit to pure love and the capacity for pure love. I think wherever you get it from, it's boundless. Now you may lose it along the way because of conflict, but that's different than love. I'm just talking about that feeling of love. That it's not like it's a pie. It's like I have so much love, and if I love you this much, then I can't love you at all. Because that's all the love I have. Love isn't like that. Love is bigger than a quantity. In my opinion.
Conditional or unconditional.
Right,
I'm
there's
talking
different types of
unconditional love here. I'm just talking pure love. I'm not talking conditional love. I'm not talking relationship. I see relationships very different. That's a different ballgame. And you don't lose it. No matter how much you give away, you don't lose your ability to love, or you don't lose love. It's just there. So, I would put it in plus.
I would, yeah, say love is pure energy. And maybe that doesn't fit into this equation, right?
So it's like maybe love is just like you're the channel of the energy. You're not keeping it, but maybe it's not yours in the first place.
I think you're just open to love. I think that this is my personal belief. I think what your mind creates your own reality. If you look for love, you will find it. And if you look for something else, you will find it. You will find what you expect to find. And it's the Buddha said, first thought, then the word, then the deed. It all starts in the brain. Love just starts there. Unconditional. There's absolutely no limit to it. You allow it to be expressed through you.
So what happens when we are afraid?
You shut down.
Not necessarily. There are definitely people who are fully living life when they're afraid.
Oh yeah.
They actually love it. Like, and I'm adrenaline junkies are probably the perfect example, and I'm definitely one of those. So
yeah, I mean, different people can experience these things totally differently. For some people, fear might open up possibilities because it might be a motivation for you to do something. Or is that kind of how you see it?
Yeah, to a certain, it excites you, right? Because
Right.
whenever you get excited, it all comes from the same source. And then depending on the context, that's when you define like whether it's fear or love or anything like that.
Sure.
And so I see your mindset on your idea of whether or not something's good or bad, and whether or not something can produce something for you. If you see fear as bad and it can't produce anything for you, you're going to shut down. But if you see fear as good and you use it to produce something for you, it's positive. Sure.
Well, yeah, I think that's right. I mean, fear has a healthy place to keep you alive. You know,
And I
but
think
it controls it, doesn't.
we're talking about different things. I mean, I think fear, the kind of fear you're talking about, I also enjoy. You know, I don't look at it as fear, I look at it as danger or risk or adrenaline or going too fast, whether it be, you know, in a car or on the beach or whatever. Which is a highly pleasurable activity. Right. But when I think about fear in this context, I think about more the fear of the other or the fear of losing my love, you know, things like that. And I don't like that. I have this kind of fear.
For me, it has to do with what we already talked about, is the attachment.
Yeah.
That to me is kind of the central mental state, that how, whether you're attached or not attached, you can be attached to another mental state. Like if you're attached to fear, then maybe that's not so good. And if you're unattached and can experience it freely and have it invigorate and energize you, then that's when it's going to be like that dynamo. And the attachment, I think, is fundamentally entropy decrease. Because like you're saying, you're tied to someone, it just limits what you can do. If you're attached to something, it's going to change how you're able to think of it. And when you're unattached to something, or unattached to the outcome of something, it's much easier to look at things from lots of different angles. That's how I would see it. Well, we've had some rich discussion here, which I like. We're gonna kind of shift gears. Let's see if we can get to this a little bit. So, I want to ask a question. I can erase this. This is still up here. What is the ultimate destiny of humanity? Is a big question. The ultimate destiny. I'm gonna break it down for you. We're gonna make it simpler. Okay. We're gonna say macro state 1. 1 is survival, and macro state 2. What's that gonna be? Not survival, destruction or something. Complete annihilation of humanity. Or we could even view this in terms of life. Like, what is the destiny of life in the universe? To survive or to be destroyed? So I'm talking about over long time scales. So in like 4.5 billion years, I think, maybe 10 billion years, something, the Earth is going to be evaporated by the sun because the sun is going to die and consume the planet. So my question is, at that time, what is our destiny? And how can we tie it into, like, maybe not the energy, but the entropy at least? Yeah.
Like I said.
Oh, he raised his hand. So.
Yeah.
Ryan, go for it.
Well, I took, what did I take? Philosophy of religion, and apparently contemporary physicists think that all space is going to like shrink back in on itself, regardless of like whether the sun is going to engulf the Earth. Like all space is just going to like go back in. So it seems to me that says, if you agree with that, that destruction is inevitable because like space itself is just going to
Collapse on itself.
cease to exist. Yeah.
Okay. Maybe we just gotta find some new space.
I don't know. I've always had the theory that when everything goes into a black hole, it comes back out some.
Yeah, no, I mean it comes back out, but could like survive that. Yeah.
Okay, let's
2 billion years.
reel ourselves in from the fate of the universe and just focus on like now what is the relatively short term fate of humanity.
Okay, so, the relatively short.
relatively short in like the lifespan of the sun.
Okay,
That's
so in
relatively
that,
short.
in that case, then you would have the ability to alter the physical reality of mankind to the point where we no longer resemble humans, right?
Yeah, sure. And we would count that as survival.
That would be survival,
I would count that as survival.
but we're no longer human.
Sure.
The human
Yeah,
race
our
is-
lineage is surviving.
Right, but the human race no longer exists, so therefore it was destroyed.
Okay. Yeah, that's interesting.
So,
So
we
what-
have survived as what we would call our collective existence, but the collective existence has changed so far from its original that it no longer is the original, and the original is destroyed.
Right. Sure. Yeah. I mean, I would say like there's no way that we'll survive in our current form. That's just not how things work. There's way more ways to be different from our current culture than there are for our current culture to exist. So over long enough time, and our biology as well, and that's why things like evolve over time, is because that entropy is still kind of a disordering force. It's mixing things up, you know, tinkering and like changing the course. But you're saying you think that the lineage will survive.
Yes.
And why do you think the lineage as a whole will survive?
Well, there's many examples of, I mean, if we came from one organism, right, then there's been, as far as we know, 5 major extinction events which wiped out more than 90% of all life. All life. So we're very resilient, regardless. There's tardigrades out there that are flying through the universe, and if they started with us, which most likely they didn't, but if they did somehow, then they're also part of our lineage as well. So, and they're some of the most like resilient creatures in existence. And because we have the knowledge to find all of these things and figure out, instead of just let nature take its course, we actually have the ability to predict and things like that. And with predictive capabilities increasing more and more and becoming more accurate, not only will we have almost kind of like an insight into the future with AI technologies, as long as that doesn't completely wipe us out, and all of these other things, that we can build so well our own system that our system is survivable enough to live in basically.
Yeah, that's what I would say too, pretty much. I think that the destruction case, there's almost no ways that that can happen. There's like complete nuclear war, or like a meteor hitting the Earth or something, or like that's pretty much it. As like there's maybe some other ways that humans can totally annihilate each other.
Well, the sun blowing up.
Let's, yeah,
That
if we're
happens
still like not
That's almost
planning ahead.
That it's not, right?
Well,
There's
yeah,
not-
but-
there's not a variable that makes them blow up.
Well, there is variables that could increase its or decrease its lifespan. Say in 10 years we decide to start ejecting trash into the sun. That would actually increase its death rate. Yes.
That's not gonna happen. So like in the astrobiology.
Into the ocean, don't worry about the sun.
Until it's all full, and then we shoot it into the sun.
In astrobiology, which is like the study of extraterrestrial life, which actually happens in like mainstream laboratories, people who don't believe like the Earth has been visited by aliens but still study extraterrestrial life somehow. They basically
They don't believe.
right, yeah, okay. They classify a civilization based on like how spread out it is across the universe, and the idea is once it's spread out enough, it's pretty much impossible to destroy. So, for example, on the Earth, we could be destroyed by nuclear war, the sun, or like a meteor maybe. If we form a colony on another one of our own planets, then we would need like 2 nuclear wars and 2 meteors and still just the same sun, I guess. But once we get outside of that, there's almost no catastrophic events that are capable of wiping out a civilization, which is why in my mind, it's pretty much like a given that there's intelligent life elsewhere. Because it only takes one civilization to survive, and then if let's say that there was another entire generation of suns that died before our sun even existed, if even one of those survived, it's now like 10 billion years later, they would be everywhere. There would be conscious, intelligent life everywhere. So I would say that the destruction case actually very unlikely, just in terms of the amount of like micro states and macro states that would happen. There's like very few ways that you could arrange things on Earth to destroy people. Now, certainly, we could eliminate like half the population with disease or famine or like plenty of things, but to get every single last person is not likely. But you obviously are free to believe as well. Okay, now we're going to get into something totally different, which is related to that systems introduction we had at the beginning, which is, does anyone have the time, actually? I have 1 minute for this.
8 o'clock.
Oh, dang. This was only supposed to go till 8, right?
8:30.
Oh, 8:30. Great, okay. Okay, we're going to talk about fractals.
And you all have the right to leave on your own free will. Slow down.
That is true, yes. I can be the last one here for somewhere. Okay, so fractals and systems. We're going to talk about how human beings arrange ourselves. So what are the different social structures, which are also called like invisible structures, are at our disposal for creating the most badass future or the worst future that we can imagine. And these structures are like basically types of systems. So it's like a fractal. Well, I'm rambling. Someone tell me, what is a fractal? Yes, Ryan.
A pattern in which the most macro characteristics are emulated on the most micro level.
Okay. I like that. Does anyone disagree? Have anything to add? Want to put it in a different way?
Repeating pattern,
Yeah. The repeating pattern.
like, what's it called? It's like 1 and 1,000 and 10,000.
Oh, exponential.
Exponential? Is it exponential?
Yeah, it can be. Has lots of exponential properties, certainly. Yeah, so the basic definition which Ryan gave is that it looks, I'm going to put it in simpler terms, something that looks similar to itself no matter what scale you look at it. So if I look at it at like a huge scale, it'll look similar than if I look at it at like a microscopic scale. That's something that is a fractal. So that's called self-similarity. And it turns out that pretty much all of the systems and structures that exist within life are fractals. And they're fractals nested within fractals, or fractals that have other fractals like hanging off of them. So none of them are like one clean, perfect fractal, but they have lots of, they're like made of different fractals. Another property of fractals is that they're space filling. Space filling, which means that they kind of grow to occupy all available space. And another property of fractals is that the endpoints, which are also called like terminal units, but also called endpoints, are the same, no matter how big it is. So I'll explain that once we get into the examples of fractals. So there's basically four, let me get rid of this, 4 types of fractals that we see in nature and in society. 4 different shapes of fractals, you could say. What is one of them?
Hierarchy.
Hierarchy, yeah. Hierarchy. So what is an example of that in like the physical world?
Like a business structure, CEO, and then under him the board of directors. And
Sure.
under them.
Yeah, so like a top-down business or any other top-down organizations. What about in like physical things, like a living thing, a living system?
Oh,
Food chain? Yeah, you could.
Genes.
Food chain could be one. Food chain is definitely like a nested one. What were you?
Genes.
Genes, like genetics?
Yeah,
How so?
genetic line. It's the hierarchy of your DNA.
Oh, like a family tree? Yeah, totally. So this could be a company, family tree, or yeah, actual tree. Actual tree. It could be a watershed, although it'd be like flipped upside down. And a tree obviously is flipped, it's like 2 of these, you know, you've got the leaves and the roots. And so what it would mean, like in the example of a tree, when I say that it's self-similar, is that if I look at like the tip of a branch of a tree, it kind of has the shape of the entire tree. And that's because it's following the same rules. So it starts with one line, that line splits into 2 lines. Each of those lines splits into 2 lines. Each of those lines splits into 2 lines. So it's obeying a very simple rule over and over and over again. It's space filling, which means that in the tree case, it's like at the canopy, over long enough time, this will turn into, even if it's made out of lines, it will turn into a surface. So like the canopy of a tree looks and behaves like a surface, even though it's made out of a lot of things which are not like one surface. So that's space fillingness in a tree, and the endpoints are the same. So this would be like the tree's leaves are the same no matter how big the tree is. As the tree grows, what the endpoint of the leaves or the roots do doesn't change no matter how big the tree gets. Something else I want to say about that, I don't remember. Maybe I'll remember. What's another hierarchy?
Social structure of like different animals, or like for wolves, for example, alpha,
Sure.
beta.
Okay, what's a different type of fractal? What? So we've got 1 out of 4.
Spiral.
A spiral. Okay. That looks something like this. Spiral. And where do you see that in nature?
Like the flowers.
Flower, seashell. Okay.
Wave, galaxy.
Shell, wave, galaxy, water, all over the place.
Hairstyles.
Okay. How about in a social environment, or like for your own self? Are there any things about any invisible structures that humans work within?
Habits.
Habits, how?
So habits can kind of revolve around the central structure, and they can spiral out, and they like certain habits will take priority in terms of that. Like for studying, for example, if you're studying, like part of your studying will be less important, and that would be on the outer edges. That's where you get less energy, whereas the stuff that you need to focus on and have like weaknesses on, that's where you
Okay.
put most of your energy. So it like kind of spirals around
Gotcha.
that.
Interesting. Okay. Cool. Anything else? I would kind of view habits from like a time perspective. Like if this is like the beginning of time, and as I go along, time is increasing. As I continue the same habit over and over again, the habit gets bigger and like wider, like more secure, more encompassing, something like that. Yeah, I would also see this in terms of like my personal growth. Like, for example, again, going forward in time, let's say that each angle is like a different aspect of my life. So at this angle, which would be this line, let's say I'm really concerned about my personal development. And then at this angle, right here, maybe I'm concerned about my like professional development. So what I do over time is I'll shift between these different phases, and then I like come back to them. But when I come back to them, I now have all the experience of all the other phases that I've built upon. So I come back from a wider perspective. I have gained new insight into my life. And so while it might seem like I'm going in circles when I question everything that I'm doing, like every 3 months, I just have to trust that I'm coming at it from like a wider perspective every time. And that I'm not going through the same process, but rather going in like this spiral process. In all these biological examples, this flower, well, not in all of them, spirals actually come do lots of different stuff. But for the flower and the seashell, it spirals out because of how it grows. So it's growing from this edge right here. And so it's getting bigger and bigger and building off of what is already built. And so that's why, like, if you take 1 month of growth for a large snail and compare it to 1 month of growth for a small snail, the large snail can grow more because it's working with more already. So a way that I would translate that to the social realm is like when you're doing organization building, for example. Let's say I start right here with just myself and one idea, and I want to sustainably grow that idea. I could try to get like exponential growth right away, or I could use small solutions and work with what I have easily available to me. And over time, maybe by the time I get here, I've got like 3 people on my team. And then 1 other year passes and I've got like 7 people on my team. I'm like slowly building with what I already have instead of like trying to jump to the end. It's like sustainable growth based on what was already grown, basically. Okay, that's 2 fractals. What is a third fractal? We got 2 left.
In a straight line, if that's it?
Straight line. Yeah, it is. I mean, it has some of the properties. It certainly has self-similarity, and the endpoints are the same, no matter how long the line is. I don't know if it's really space filling, but
You know, when I think of fractals, I mean, I'm not a mathematician or a physicist, obviously, but I think of combinations of straight lines, you know, octagons and triangles and things like that.
sure. Yeah, like the hierarchy is like built off straight lines. All you do is turn 1 straight line into 2 straight lines, and 2 straight lines into 4, and so on.
Spiral is just one straight line.
Yeah.
Or, well, it's a line.
Yeah. It's straight if you look at it from a different perspective. Yeah. Okay, but how about in terms of like a big structure, like a system? What kind of structures can systems have?
Would a crystal be?
Crystal, yeah, one of my favorites. Actually, they're all my favorites. Crystal, okay. A crystal is a fractal. A crystal has the property of being very boring and very interesting at the same time. It's very boring because it's the same everywhere. And if I put a new object into this crystal, generally it's very limited in terms of where it can go. You know, it has to be, this is just like a square grid. Obviously there can be other like grids. But it looks the same because if you look at, if each of these is one atom, they make a square. And if I had a chunk of this crystal in my hand, it would also be a square. So it's self-similar because it's building off the same rules that something has to be placed relative in an angle relative to other things. So where do we see this in nature? Crystals, obviously. Okay. Where does anyone have any other places we would see a crystal in nature other than like a rock crystal?
Well, in a beehive, for example, like the bees in beehive.
Totally. Or like the hexagon shape of the honeycomb. That's a good one. Definitely. How about in a social setting or in like an emotional or mental setting?
Social would be like nationalism, for example.
Okay. Why?
It's a similar mindset. It's self-similar. It's space filling because it wants to expand. And then it's, what was the other one?
Self-similar, space filling, and the endpoints are the same.
Yeah, well, I guess you would call it the endpoints talking points. They're always the same.
Or in like a social system, I would consider the endpoints like the individual people within the system.
And they're typically the same because they hold the same, their self ideas or self.
Yeah. So I think that's a great example of a crystal. Really, any ideology be a crystal, something that's subject to not change.
That like is similar though, because there are definitely like disunifying ideologies as well.
Sure.
Like decentralizing, so centralizing.
Okay. We're gonna come back to all these from like the thermodynamics perspective in a second. What's the last one?
You know, we even talked about that in terms of crystallize our thoughts.
Oh.
As naturalists for any group of people.
Yeah. No, we use the same words to describe physical and non-physical things. Okay, the last one.
Raindrops, snowflakes.
Snowflakes is the closest so far. It's a web. A web structure. Yeah, like mycelium or the human brain. What are some other ones?
Webs.
Spider web. Spider web. Brain.
Satellites.
Internet. Satellites. How about like a social thing? I guess the internet is kind of a social thing. What about like an organization structure?
Social media.
Social media, anarchy, sure, or like some other non-hierarchical thing. There's probably
Bitcoin.
Yeah, totally. Lots of different webs. Okay. It's self-similar because it's like if I look at my brain, for example, it's made of these little neurons, which are like, these little things, kind of like that. And it's just kind of got this web-like structure. And then there's entire pathways in my brain that also have this same kind of structure. Like my frontal cortex is in a web with my visual cortex, and they're like connected in this kind of web-like fashion. Okay, now we're going to talk about what these different fractals do in terms of energy and entropy, and how that relates to what they're good at doing and what they suck at doing. So, how does a web? What kind of flows does energy have within this web?
I'm sorry, say that again.
What kind of flows does energy have inside of the web?
You kind of move like anywhere.
Yeah. Okay, so energy goes anywhere. Brian?
I was going to say it has to first go through the adjacent nodes before like going to the farther nodes.
Okay, so yeah, it has to move through adjacent nodes. Okay, it doesn't necessarily have to be linear. Like I could get to this node like in a super I guess only this one connects. Kind of like backwards, you know? But most webs, there's lots of different ways for energy to get anywhere within the web. There's like, this one is not very resilient, but I can make it more resilient. Now it's more resilient. There's lots of ways for energy to travel between any of these two nodes. There's lots of different pathways open for energy to move around.
That means there's an equal amount of opportunities for those pathways to be closed as well.
How so?
Well, every node, every single point you add is a point of failure as well.
Okay.
It's also a backup.
Well, it's both. So as long as it's working properly, it's backup. Because if it's not, then it's nothing.
Right.
So yeah, for every point.
Sure. How about the web? Does this allow for energy to become super concentrated easily?
No.
Why?
Because there are so many pathways.
Yeah.
There's so many there's like so many places that it can go,
Mm-hmm.
and so it would be more likely to go.
Right.
out those.
Yeah. It's easy for energy to spread out here, which is why we see this in kind of egalitarian social structures or like an anarchist structure. And the idea behind that is that no one has power over other people, which is a form of accumulating energy. What about from an entropy perspective? How many different ways? Let's say I was going to place a new node in here. How many places could I place it? Yeah, I can place a new node anywhere at all. And any of these nodes can kind of like move around also. They're not totally tied to a node that came before it. They're kind of all independent of each other, but still in this network.
So they don't have to be equidistant?
No, they could be placed anywhere.
And can each node connect to any other node?
Probably, yeah, like through other nodes.
Well, I mean,
So if I put a node way over here, it's not going to be easy to connect to this one without going through other nodes.
right, but if you placed one within that accumulation of 4,
Mm-hmm.
then all 4 of those could then connect to that one node if they're close enough.
Right.
So even one spot could be 4 or 5 different possibilities or more.
Yeah, they can grow in different directions. So this works really well when the system is sufficiently small, because if it's sufficiently small and let's say there's an energy source like food over here, it's kind of inefficient. Although the food will eventually be distributed evenly, it's not efficient in how it does so because there's so many different pathways that it can go through at each junction. The energy kind of gets muddled and confused. So if I really wanted this energy to end up over here, it's hard to make that happen. And this makes webs not very good when they're big, because the bigger it gets, the more connections there are, the more ways there are for energy to get lost inside of them. And there's the more ways there are for there to be confusion inside of them. Like for people in a social structure, since everyone is kind of connected, let's say we have this triad of people over here that are working on something within an organization. They might all be on the same page about what the mission of the organization is, but these 3 people could easily have a different idea of what the mission is, and there's no way for you to like enforce the mission from any direction without having this tangled web of relationships in the middle. So when you try to change the operations of a web, it is very hard because every node is kind of independent And there's so many possible relationships within all of them. So it's got good and bad. Hierarchy. How does energy move through the hierarchy?
Only two ways.
Yeah, it can go up and down, basically. I mean, that's a little bit of a simplification, but that's basically it. Energy up or down. So it's pretty unidirectional. You know, in a case of a tree, energy is hit the leaves, and that energy then like goes down into the tree. Or in the case of a watershed, you know, all the water goes downhill. Energy goes up or down, so it can distribute energy in a couple of different ways. How about the entropy? If I was going to add a new node, like a new endpoint here, how many places are there?
Only the outer edges, right?
Yeah, I can only add stuff here and here. So it's pretty low entropy. There's not a lot of possibilities for change. And what you do early on has a huge impact in terms of what's possible later. So for example, a tree is going to have a first branch that eventually might turn into like a second trunk of the tree. And that very first branching then has a huge impact on all the leaves that can come from that tree later. So that maybe is not so good. But what's good about it is that since this energy has very straightforward flows, it's super efficient. If I want to get energy from here to here, I only have one choice at every step of the way. So it's very obvious how that energy should flow. And likewise, if I want to get energy from here to all these tips, again, I have one choice at every step of the way. So that leads to a lot of efficiency. But then what happens if, let's say this is like a decision-making funnel, like the trunk of the tree, for example, has a huge impact on like what the rest of the tree can do. Why is that bad?
Because it's only one point of failure, so if
Yeah.
it fails, you're dead.
Yeah, if I cut the tree and if I cut the trunk, all the leaves will die. Whereas in the web, I can cut any connection and all the nodes should still be able to mostly connect to the other nodes. So hierarchy is not resilient, and it's because their entropy is low. There's not very many places for new things to happen, and everything is based on what happened in the past. Now, of course, what's really great about these is that they never exist in isolation. So, for example, my brain is formed as a web, but the rest of my nervous system is a hierarchy. So right at the weakest point of the hierarchy of my nervous system, which would be where you could cut the trunk, I have a web. So I have built in the structure of my body ways of getting around the lack of resiliency here. It is still resilient in that if you cut my spinal cord, like I'll be paralyzed. But in terms of like decision making and like how I can move my limbs and stuff, I have much more flexibility because there's a web at the top of it. So we can nest these within one another. Okay, the spiral. How does the energy flow within the spiral here?
Pretty much
Outward
the same
or
as
inward?
Outward or inward? Yeah, there's two directions again. It can go out or it can go in. So similar properties to this. How about the entropy? If I wanted to add a new thing onto the spiral, where can it go?
Anywhere along the current line.
You like out this way?
So only one place.
Yeah, it can go at the end. It could maybe go at the beginning also, like build tighter inwards. I don't know. No, that definitely like happens. That's actually how flowers grow. They don't grow from the outside, they grow from the inside. Whereas a shell would do the opposite, it would grow from the outside, I'm pretty sure.
If it was growing from the inside, would it push the outside?
Yeah, exactly. I mean, that's why flowers have those spiral patterns. Is the new like seed or whatever, like pistil or whatever structure of the flower is growing in the center. It's pushing everything out in this spiral, and so you get like when you look at all of the seeds, like in the sunflower, you get a spiral. Kind of the spiral has similar properties to the hierarchy, but it's even lower entropy. How about the crystal? What is the energy doing in this crystal?
Staying very still.
Staying very still, and does it probably have a lot or not much?
Energy?
Yeah.
Yes.
Yeah. It could be either. It could be a lot, or it could be not very much. But it is not easy to change. Not easy to give energy. So that is why, like a diamond is really hard, or like lots of crystals are like really hard, is because it's hard to transfer energy into them. They don't like break easily. They're very resistant to changes in energy. How about the entropy? Are there lots of places or not places to put stuff?
All the edges, right?
Yeah, you can put stuff on the edges, but there's still only a set number of places that they can go. You know, they couldn't go like in between these two in this particular case. So the entropy for a crystal is quite low. Quite low. So what crystals are really good at, since they don't accept energy very easily, they transfer energy. So if I put something like, let's say this is a prism, and I put light into it right here, I know exactly where that light is going to go every time. It's going to like come out at some angle over here. Maybe it'll like split up into a rainbow or something. And the angle that it comes out at relative to what it comes in at is always going to be exactly the same. And it's based on the geometry of the components inside of it. So the crystal transfers energy in a super predictable way, which is why, for example, our fiber optic cables that our internet is based off, or our phone, or our computers, these are all built out of crystals. And it's because they transfer energy super readily. But they're not easy to change. Like, if I have a fiber optic cable made out of one material, and I want it to suddenly do something different for me, I'm pretty much going to have to get a new material. I can't like change the material very easily to make it have new properties. So in a social context, the crystal is like a stabilizing structure. It might be low entropy, but it allows you to have predictability. So I like combining the crystal with the web. So let's say earlier we were talking about the problem that these different nodes would have different missions. If at the outset you crystallize the mission of the organization and you make it very clear and very difficult to change, then all these people are going to be on the same page if they're working from that crystal of whatever the mission of the company is, or the values of the group, or whatever. So having some kind of like crystallized mission is a way of getting around the problem that the web faces.
Like you almost can't join the crystal unless you're the same shape.
Right.
If you're a different shape than the
Right.
crystal you want to attach.
Right.
But that's
Yeah.
the same thing as a hierarchy imposes that shape.
Yeah, but if maybe you have a web that creates the crystal in the first place. That's a way of making it so you're not like being forced to do something like in the hierarchy. Like in the hierarchy, it's probably this person right here that has the power to change the crystal, and that's going to affect everyone downhill. But if as a web, like the first thing that you do is create a crystal together, it might take forever and like be really messy. But if you succeed and like get that nugget, then it's going to allow your organization to grow so much easier. Because then someone, like for example, I used to do more organizing with the Permaculture Action Network. They operate in this kind of web-like structure. And people would ask me all the time, like, oh, I have this idea for a project. Is it something that you guys can help like collaborate with? And at the beginning, it was very ambiguous what was allowed and not allowed, what's within the scope of the organization or not within the scope of the organization. And since it's a web, there's not like one person that I can ask to get the answer. So it was like kind of very confusing. But what they did is they crystallized the mission and made what they do very specific and made it very formulaic. So like you want to organize an action day, we have a 5-page document that tells you how to do it. And obviously you can kind of do it in your own way and like interpret the document your own way, but it outlines for you how it's basically done. And that makes it easy for new nodes to join, and it's not confusing as to whether something's like inside the scope or outside the scope.
The military's a lot like that.
Yeah, the military is kind of this crystal hierarchy.
But also web too, because you have decentralized areas and nodes as as well.
Yeah.
So, I mean, that's why you have 4 branches, right?
Right.
So that if one gets taken out, you can still use the operational abilities of the other ones.
Sure.
Take up the slack.
Yeah. I mean, all of these structures have weaknesses and strengths, which is why we see them nested inside of each other, or why we see like a hierarchy that goes both ways. You know, like my circulatory system is like a hierarchy that not only goes both ways, but then like connects the ends to each other. So it's like a big circle kind of thing. Or my brain here and the rest of my body here. You nest them within each other to take advantage of the strengths of one and try to like mitigate the weaknesses of the other ones.
What would be like a social example of a spiral? Like a social system.
Yeah. So I would see this a spiral in terms of like movement building. So or cultural shifts happening. So like a revolution could be an example of a spiral, where or a new religion. Yeah, where you start with like one idea or like one small core group of people that's working on something, and then over time they build on what they've created and they keep that momentum going, and it grows and grows and grows bigger until they're the dominant structure. They've become space filling. So yeah.
So that would be like maybe like the ultimate goal of like the grassroots.
Right. Yeah, I would see that. I mean, not everyone people in the organization might not necessarily see it that way. Like you can be in a grassroots organization and not like be trying to transform the entire society. But I think oftentimes that is what people do, and activists and young people especially like come at it with this perspective of like, oh, we're going to change everything. And
2 things come to my mind immediately. One is Tiananmen Square, small group
right.
comes into the eye of the storm.
Yeah, you know, there's like protests or like revolutions, you know, any movement, I would say, like, and any organization that's successful over the long and scales, I would say, generally works this way. Like companies have a pretty finite lifespan, and I think a lot of that is because like the way it's operated is based on debt and like investment, which is not this stable long-term structure. It's a way of accomplishing something perhaps very quickly, but you can easily run out of steam quickly because you're not building based on what you've actually created. You're taking debt or you're getting like an investment. So you're kind of building based on what someone else has created and hoping that you can like create enough to keep yourself going. But often that's not what happens. So I would say successful organizations like Walt Disney, for example. I love Disney, but you know, started with this one guy, Walt Disney, who was a brilliant animator and created a character that people loved, and like just it spiraled and like grew based
People wanted
on
to contribute their own thing to call it Disney. They wanted to like put their energy into what Disney is.
right, exactly. He starts attracting other people. People are like, oh man, this person is creating videos that the world has never seen anything like them before. So I want to work with them. And so it attracts like the brightest minds. And you know, maybe now they're not as like running like as sustainably. I don't really know. I mean, it seems like they're not going anywhere anytime soon.
So using the image of the spiral, as the spiral expands, does the line become thicker?
Generally, I would say no. Yeah, but it's kind of unclear what the line is in the spiral too, I would say. But in the spirit of like the terminal units being the same, the line would be not thicker. But maybe it'd go, I don't know.
What would the thickness of the line represent?
Yeah, that's my question. What does the thickness represent? It's going to
Like
depend
if
on.
one person is moving in the line and then it becomes 2 people,
Right.
the line is thicker. And then it becomes 3 people and the line is thicker, and
Right.
then they have more like outreach.
Yeah. Yeah, I would view like the number of people as just like the distance from the center. So the further away, the more people. But it could also just like be the thickness. And as it goes out, like this whole space could be filled up on the inside. And it's like filling up more and more space out here, you know? So it becomes thicker that way.
I think the line would represent yourself though, and the people would represent the space in between on the spiral. It would be like more of a shaded line, just because the line typically starts with one person, right? And so that's
Yeah.
how I would interpret that.
Yeah.
That's an interesting.
Yeah.
Yeah,
As long
exactly.
as the two endpoints look the same, they
Yep.
can be different sizes.
Right.
Yeah, but one person can do a spiral with themselves too.
Yeah, totally. As we talked about at the beginning, it's all about the lenses that you're looking through. Like none of these things are like these are mental tools that we're using to try to be better and like make changes that we want to see. It's not like, I mean, maybe there's some like absolute truth buried in there, but I don't really see it that way. I see it more as like a method that we can use to create healthier relationships, which is why this talk is like about relationships, which are based on like, it's just about building our tools so that we can be better and do better things and be healthier and happier and all that good stuff. So if it helps you to see this line in one way, then see it that way. That's all.
So to sum it all up, everything's love.
Yeah,
Yeah.
that was the main
Nailed it.
takeaway that I was like, that's one of the important ones for me. And just like the living freely is a way for you to release energy and like equalize energy and create possibilities, like that fire. You know, people talk about a flow state, that fire within you. And it's like, in my view, it's very literally like a fire because causing energy to smooth and creating possibility outside of it. Yeah. Are there any other like questions or comments or
Thank you so much.
complaints?
I was really hoping for more strawberries.
Oh, sorry.
Should have got it.
Cool. Well, thank you all so much for coming. This is so
You're
fun.
such a good teacher. And it's such
Thank
a
you.
complicated topic.
Thank you. Yes, this is a culmination of years of me sitting, thinking about stuff.
You guys get some credit too.
Yeah. My first physics teachers, or at least my first relationship teachers, maybe. Yeah. Cool. Yeah, should we like have a group hug or something?
Does that increase our entropy or our energy? It'll decrease our entropy. Increase our energy.
Yeah, something like that. So I want to release energy. That's like, or like do some kind of closing so this energy can be accessible outside.
Like a selfie with him.
A selfie, yeah.
In front of the board.
Okay, let's take a picture.
We can all frame our bodies.
Picture, that's a good
Put our bodies around the board.
Okay.
Our faces make it funny.
No one is obligated to participate, but I would love a picture of it. Whoever wants to.
Let's put the camera on the countdown.
We could take a picture with my computer.
Yeah, I like that.
Does that work?
Oh.
Bye, Facebook. Thanks for tuning in.
See
you the next time.
What?